Hello and welcome to Physics 2012, Lab 5 Magnetic Braking with Faraday by Blake Schraube. The purpose of this lab is to collect falling data from a magnet for using Faraday's law, and this was all done through a aluminum tube. The system is the aluminum tube and the magnet. The surrounding is everything else. Assumptions we should have is gravity and magnetic force are the only forces acting on this object, and their resistance is negligible on the falling magnet. But in observational studies, this cannot be more done in real life. This can only be done through computational. Results experimental time 1.284 seconds, and computational time averages 0.45 seconds. Fundamentals and the procedure. We have Faraday's law, the entire thing that's based off of, Bias-Savant's law, which is used for some formulas, and the second, third laws, which are also used for some formulas. The procedure, we use the magnetometer app on our phone. We use that to find the north pole of a magnet. Then we record, or basically use a stopwatch to drop this magnet through an aluminum tube. We repeat this process 5 total times, making sure to stop the timer as close as possible to when it reaches the bottom to keep the same level of measurement throughout. Some results that I found from the observational study, the length that we had was about 0.3 meters. Width was around 0.005 meters. The inner outer radius was 0.025 meters and 0.03 meters respectively. The mass of the entire thing was 0.025 kg. Average was around 1.284 seconds. Mu that I found from lab 3 was 3.189768904 AM squared. Now, coding. Plugging all that data in, which is seen in the first and second screenshot here. I then calculated for the dipole, and then the flux analytics throughout. Well, d flux over dt, which is found down here, so I changed. And then I edited the gravitational force for this vector. And then on the next slide, we edit basically the current in the ring with this formula right here using the previous slide's information. And then we basically computated B field, and then the magnetic force, and then just kind of the net force, and basically the velocity and position as well of the magnet. So this is the model results. As you see, upside down, south side up. As I was doing this out, when I created this tube, the time it took in this tube was measured to be 0.45 seconds. Now, there are a few reasons why this could happen. Measurements. Sometimes the measurements were a little bit off, and that could have been the reason why. Rounding wise, you can't be precise as possible. Human error. I could have messed up with measurements. I could have messed up with scaling everything. I could have messed up with weighing everything. That could also been a thing. I did round quite a bit to get some of these. If I didn't round, maybe it would have gotten more precise. There could be something within code that could have been the problem, but those were the causes that could have been the error. Now, basically, what if the resistance of the conductor basically was reduced as close as possible to 0? How would the dynamic of the falling magnet change? It would decrease resistance, so it would increase the current, making the magnetic field stronger, which in turn makes the magnet take longer to fall. Now, what if you were to create holes or slots into the tube? How would this affect the ring currents in your model? Well, if holes were cut out, there would be less rings overall within this, which would make the magnet fall quicker because the weakening of the magnetic field has happened because of that. Thank you for watching.